This lab investigates the motion of an object moving at a constant speed without changing direction. The purpose of this lab is to investigate Newton's second law of motion. This is achieved through an experiment where weight is released and allowed to move in an environment where friction is assumed to be negligible. Additionally, a computational model was created on WebPython to simulate motion zero net force. The experiment and model results will be compared to verify that under these conditions, velocity remains constant. Newton's second law of motion states that the force acting on an object is equal to the mass of that object multiplied by its acceleration. F is equal to ma. We know that the acceleration is zero because our velocity is constant. If there is no net force, our velocity remains constant. Using Tracker, I plotted position versus time, which resulted in a nearly linear graph. A linear trend confirms constant velocity, which is expected when the net force is zero. Even though the object isn't speeding up or slowing down, forces are still acting on it. They're just balanced. Newton's second law helps explain that when all forces cancel out, the net force is zero, and the object maintains its velocity. If I wanted the weight to speed up, I'd need to apply another force. The more mass it has, the more force I need. That's Newton's second law in action. More mass means more force needed to get to the same acceleration. What if I flip the axis in Tracker? Well, if I reverse the direction of the x-axis so that the positive x became negative x and vice versa, the numerical values of the position and velocity would switch signs, but the overall motion and physical behavior of the object would stay the same. This is because when we flip the axis, we are only changing the way we define direction, not the actual movement of the object. To verify my observations, I built a computational model using WebPython. The model assumes that only gravity and normal force acts on the weight, and since they cancel out, the net force is zero. Because acceleration is defined as F net over m, and F net is equal to zero, the acceleration is also zero. What does this mean? Well, this means that velocity remains constant regardless of the mass of the object. To match my experimental data, I set the initial velocity and the position of the model to the same values recorded in Tracker. Then I use the position and update formula and while loop to continue updating both my position and velocity for my model. Here are my models. The velocity is constant while my position updates linearly. I compared my model to my experimental data by plotting both position time graphs together. The model graph is perfectly linear while the position graph is nearly linear with slight deviations. The experimental results show minor variations likely due to small tracking inaccuracies or external disturbances. One potential error was tracking inconsistencies in Tracker because selecting the center of mass in each frame was likely subjective, leading to small deviations in position data. Another factor could have been additionally, while friction was assumed to be negligible, there might have been minor uncounted forces. To summarize, while the motion in my video shows constant velocity, Newton's second law still applies. Since the weight isn't accelerating, that means the net force must be zero. The forces added on it perfectly balances out. If I wanted to speed it up or slow it down, I'd need to apply a net force, and the amount of acceleration would depend on the object's mass. That's exactly what Newton's second law tells us. F is equal to ma.